We start with a new chapter, oscillations, SHM, that means simple harmonic motion. The first point that we are going to study is periodic motion. Now, what is a periodic motion? Periodic motion is, you have learned it earlier in the class 9-10, that is any motion which repeats itself after regular intervals of time is called periodic motion, or you can say or harmonic motion. Both the terms you can use, or harmonic motion. That means the definition of periodic motion is any motion which repeats itself after regular intervals of time is called periodic motion or harmonic motion. Second point is that the constant interval of time after which the motion is repeated is called time period. Now, the motion of planets around the sun, the hands of a clock, the second hand, minute hand, or the hour hand. Third example, you can say the blades of a revolving electric fan. These are examples of simple harmonic. They are examples of periodic motion. Now, a characteristic of this motion is that each examples, we have to write the examples. First one is, you can write the motion of planets around the sun. Second one is motion of a simple pendulum or other pendulum of a clock. Okay, now a characteristic of this motion is that each particle moves along a definite circular or elliptical path repeatedly in a regular time interval. Now, the motion of planets around the sun means the motion is not in a circular path, but it is in an elliptical formation. So we can say that the characteristic is along a definite circular or elliptical path repeatedly in a regular interval of time. Now, the motion along an elliptical path is called elliptical or orbital periodic motion, orbital or orbital as you pronounce it, while the other motion is known as the rotational periodic motion. So, two types of motion we can get: orbital periodic motion, and the other one we can name it as rotational periodic motion. So, the third point, that is the periodic motion can be rectilinear or rotational or simple harmonic. Now, this point is very important. There are three types of periodic motion. Now, you can start with one of these, like you can start with oscillatory motion. You can start with oscillatory motion. Now, what is oscillatory motion? Now, oscillatory motion, we can say the motion of a body is said to be oscillatory or vibratory. Oscillatory, or the term vibratory can come. Vibratory motion, if it moves back and forth. Now, back and forth, or you can say to and fro. That means back and forth or to and fro. The motion of a body is said to be oscillatory or vibratory motion if it moves back and forth about a fixed point after a certain interval of time. Now, the interval of time is fixed. After a certain interval of time, the body is moving to and fro, you can say, or back and forth. Now, the example of this can be the wear of a sitar or any stringed instrument. When it is plucked, it moves like this. It moves back and forth or to and fro. That means a particle, if you take it here, if it moves in this fashion, again comes back and moves in this fashion, again returns back to its mean position. This is known as a vibratory motion or plain oscillatory motion. So, I repeat, this should be, this to and fro motion or back and forth motion must be about a fixed point. This is the fixed point. About this point, the body moves in this fashion, comes back to the mean position. Now, this position of the fixed point is known as the mean position. Moves back and comes forward again. This is known as an oscillatory motion. So, the examples can be vibrations vibration of the string of guitar or sitar. Anytime you can write. Another example can be oscillation of a mass suspended from a spring. That means like this. This is a spring, this is a mass attached to it. If we pull this mass down and then release it, this mass is going to oscillate in this mode. So the second example can be oscillation of the mass suspended from spring. Now a little bit of mathematical portion. What is harmonic function? That means an oscillatory motion when expressed in a mathematical form. In the mathematical form, they are known as harmonic functions. The trigonometric function of constant amplitude. Amplitude is constant and single frequency is defined as harmonic functions. Now what is amplitude, what is frequency? I suppose we have studied earlier in class 10. Constant amplitude and single frequency is defined as harmonic function. That means all the trigonometric functions, out of all the trigonometric functions, only sine and cos functions are taken as harmonic functions in the basic form. That means sine and cosine functions are harmonic functions, are harmonics. That means if we can express these forms as y is equal to, suppose, a sine of theta, that means we already know theta is equal to omega t from circular motion. You can take a is equal to a cos theta, that means a cos of omega t. Now these are all harmonic functions. Now after this, if a question comes like this, when functions are taken to be non-harmonic functions, that means these two factors, constant amplitude, if the amplitude varies, then we cannot take it to be harmonic. If it is a variable frequency or the frequency is not constant, then also we cannot take it. Basic forms like tan, cot, sec, cosec, these functions cannot be taken as harmonic functions. Only case that is sine and cos. Now we try to explain some basic terms. I know that you already know these terms. Very quickly, in short we can take if this to be the position of the particle at any instant and the particle starts to oscillate. That means to and from motion. I've already said this is position A, suppose this is B, this is C. Now first one is complete oscillation. Now this A to B, we know this as amplitude for the movement from A to B or from A to C. These are known as amplitudes. These amplitudes should be fixed for a simple or for a oscillatory motion. Now complete oscillation means the particle will have to complete 4 amplitudes. The particle will have to complete 4 amplitudes. It can be in this fashion. From if you start from B, you have to move to A, to C, then to A, and then to B again. That means 1 amplitude, 2, 3, 4 amplitudes. Again, if we start from the mean position, A is known as the mean position. So A to B, then again A to C, back to A. That means this motion. So both these motions can be taken to be one complete oscillation. Now the time taken to complete one oscillation is known as time period. Time taken to complete one oscillation. Time taken to complete one oscillation. Third point, you can say frequency. What is frequency? Now frequency means number of complete oscillations. Number of complete oscillations in 1 second. Oscillations in 1 second. We already know the equation is n is equal to 1 by t, time period denoted by t and frequency by small n. So the relation between two is n is equal to 1 by t. We are also conversant with another form, that is t is equal to 2 pi by omega from the circular motion chapter. N is equal to 1 by t from class 9-10. the fourth point we can say to be uh, frequency, oscillation or vibration, restoring force. Now this is very very important. That means the particle, when it is moving from A to B and back to A, now when the particle returns back to A, it is not doing on its own. Some restoring force is into play, which is taking the particle back from B to the position A, or rather from the extreme position to the mean position. There is a force acting on the particle which is bringing the particle back to its mean position. As the particle is being restored back to its mean position, this kind of force or forces are known as restoring force. Now from this diagram, it is very difficult to understand what is a restoring force. I can take you to the example of a simple pendulum like this. The pendulum is oscillating, suppose in this fashion. This is the pendulum oscillating. Now at this point, if the weight mg acts downwards, the tension force along the rope is in this fashion. Theta is the angle or the angular deviation or angular amplitude. Theta is known as the angular amplitude. So T you can break up into two components, T cos theta, T sin theta. Now this is the regular breakup of the diagram that you have learned, but here you will not need this diagram, but you have to draw a different diagram like this. This is a pendulum. Now this is mg. We will not break up T into two components as in this diagram. We have to break up mg into two components, that is one along T and one along perpendicular direction to T. That means if this is theta or the angular amplitude, this is theta. So this component along or opposite to T is mg cos theta, and another component is mg sin theta. Now we can write T is equal to mg cos theta. Now this is a very valid equation, because if this is not equal, or these two forces if not equal, the string will break up. The string will break. Now mg sin theta, what is mg sin theta? Does this force have any equating component? No. This force does not have any equating component. This force is an unbalanced force. We can say this force as an unbalanced force, because no force is there to balance this force. Now we all know that an unbalanced force does work. Unbalanced force is used up to do work, or used to do work. Now this work is to bring the particle back to its mean position from the extreme position. This is the force. We state it as, or name it as, restoring force, mg sin theta. Now if theta is very small, therefore sin theta approximately equal to theta we know, so the force becomes mg theta. And after this we have to derive the expression more explicitly at the end of this chapter. So restoring force means, I repeat, the force required or needed to bring the particle back to its mean position. Very simple. Now phase, this is a very very important thing. I am going to describe phase here in a very light note, but we are going to discuss phase in greater detail later in the chapter. Now what is phase? Phase of a vibrating particle regarding its displacement and direction of vibration at that particular instant. Is the state of vibrating particle. Phase of a vibrating particle particle at any instant. At any instant is the state of the vibrating particle regarding its displacement and direction of vibration at that particular instant. I repeat the definition, that is, phase of a vibrating particle at any instant is the state of the vibrating particle regarding its displacement and direction of vibration at that particular instant. That means the position of the particle at any instant of time. Now if we can take one simple Example, like the particle moving in this fashion, to and fro motion. The particle can start from here, the particle can start from here. When the particle starts from here, we will take equation with sign, SINE sign, or trigonometric sign value, sign function. If the particle starts from the end, we can take it to be cos, because you all know the value of sine 0 is 0. That means the particle starts from the mean position, whereas the value of cos 0 is 1. That means one amplitude has already been traversed. Remember this, whenever the particle starts from the mean position, the equation will be of sine, y is equal to a sine theta, and for this y is equal to a cos theta. This side also cos. Extreme position means cos, mean position means sine. Now, if the particle does not start from these two positions but some other position here, or rather we can say, when we start to count the time, that starting point will be known as the starting position of the particle. If the particle is moving in this fashion, and if the particle, when the particle is at this point, we are starting the stopwatch. That means we are taking into account the starting position of the particle is this position and not this two. Now this will be known as the initial phase or epoch. So the phase angle at time t is equal to 0 is known as epoch, or initial phase. So the equation can be written it like this: y is equal to, if you start from the mean position or take into account the starting of the particle to be this position, this odd position, and try to write it with respect to the mean position, then the equation will be like this: a sine of omega t plus phi. Now what is phi? This phi is the angle. Now looking at this diagram, you do not see any angle. So we have to transfer this type of diagrams into circular motions and then discuss these things. So if the position shifts from mean position to the extreme position, a shift of pi by 2 takes place, a shift of pi by 2, because one complete oscillation means 2 pi or 360 degree. That means from this position to this position is 90, again back another 90, another 90 on this side, and back to the mean position. That means another shift of 90. So 4 90s make up one complete oscillation. That means 360 degrees. Now the particle starts from here. Suppose the length is or the amplitude is 2 centimeters, and the particle starts from the midpoint. That means the angle shift will be 45 degrees. That means for 2 centimeters, the shift of the angle is pi by 2 or 90. So for a shift of 1 centimeter, the shift will be 45. So the value of phi will become 45. Now we can draw the graph. If this is the graph for a simple harmonic vibration, that means this graph is a sine curve. You all know that this graph is a sine curve, whereas this graph is a cosine curve. Now if the particle starts from the mean position, this will be the graph of SHM. If this is the graph, then the particle will obviously start from the extreme position. That means already one amplitude has been traversed. So this is a cosine equation, sine equation. Any one equation you like to introduce in your equations, provided the motion starts from the mean position and the extreme position. Now we have to convert this motion into a circular motion to understand the phase in a greater detail. So this one is 0 degree, this is pi, this is 2 pi. So this is one complete oscillation. If you draw a dotted line, this part means one complete oscillation. If you take this to be the mean position to extreme position, back to mean position, again onto the other side, the extreme position, and back to the mean position. So this can be drawn like this. If the particle starts from this position, it moves 1/4 of the circle, means it has moved up here, extreme position. Going downwards to this position means the particle has moved to this position. So this is a shift of pi. This is also a shift of pi. Similarly, this part we can get in this fashion also. So one complete oscillation represented by sine curve can be converted to a circular motion also, to understand the angle, because if we look into this we get the value of the angle 0 to pi, pi to 2 pi. 0 from this is, if this is 0, that means the line of mean position, shift of pi, another shift of pi, 2 pi. So if a particle starts from this position, or rather you can tell that when you write the equation of the simple harmonic motion, when it is starting from this position is sine, and from this position it is cosine. Extreme positions, these are two mean positions, half positions. So if the particle starts from this position and moves towards the mean position, so the displacement or the starting position of the particle is 30 degrees from the extreme position. That means the particle is somewhere here and moving towards the mean position. Particle is somewhere here moving towards the mean position, and a shift of these two positions from the extreme position to the position of the particle at this instant of time is 30 degrees and moving towards the mean position. Now how do we write the equation? Now y is equal to, the general equation is like this: y is equal to a sine of omega t plus theta, or rather phi. Here phi is known as the phase angle. Phi is known as the phase angle. So the particle starts from here and is moving away from this, but it is moving towards the mean position. If we can write the equation with respect to the sine and cosine as well. Cosine means a cos of omega t plus phi. Now first try to write it with the help of a cosine equation. Y is equal to a cos of omega t minus pi by 6. 30 degrees means pi by 6. Now why did I write minus sign here? Because the particle is at this position and we are trying to write the equation with respect to the cosine form. So the cosine form is in the backward position. We have to bring the particle back to this position to write the equation. So how much angle we have to take him backwards? That is 30 degrees or pi by 6. So I have subtracted this from the value of omega t. Now if we try to write the same equation with respect to the sine function, we can write it like this: y is equal to a sine of omega t plus pi by